So our primary purpose today is we spent all of Friday looking at the flammable definition of solids and dangerous when wet materials. We looked at, in particular, the flammable metals, the ones that are in that first group of the periodic table, the alkali metals. And so we're going to start today focusing on some of the metallic materials that are just combustible. They're not quite as dangerous, but they do have some flammability characteristics to them. And then we're going to move into some other kinds of materials that have either flammability or water danger kinds of hazards to them. And so today's lecture will focus on those. Friday's lecture will focus on kind of the last groups of materials in this category. And that will be the end of chapter 9. So when it comes to combustible metals, what we are talking about here are some very specific examples. Things like magnesium, zirconium, titanium, aluminum, zinc. Now, these metals on their own, if you have a sheet of them, chances are pretty good they're not going to ignite very easily. They might ignite if you bring a hot enough source to them. You know, we know that magnesium, for example, if we have it in like a strip form, will burn if we put it into a hot fire. But for the most part, the dangers that we associate with these are when they are in their finely divided forms. Again, the finely divided forms that we get here are things like shavings and powders. Those are the ones that we need to be more readily aware of because those are the ones that are capable of self-ignition. And these are forms that we can create inadvertently through our work on these metals. You're grinding on aluminum, the grinder is going to create friction and a considerable amount of heat. As you're grinding on it, the aluminum is going to flake. It's going to form shavings. You get it hot enough, you get it the right certain situation, that aluminum goes up and burns. And if it's anywhere near your face, you're going to feel it, especially if you're not wearing the appropriate protective equipment. So with all of these, we're not necessarily concerned with the bulk form of these. Magnesium, if we have a large enough section of magnesium, it's not going to ignite terribly easily. Even if we bring a pretty hot flame to it, there's just not enough surface area to react with the oxygen. The heat's going to get dissipated. We don't have to worry about aluminum foil spontaneously igniting. But in the proper circumstances, yes, there are some places where we can see self-ignition, and that's why we have to be careful. Now, for any of these would be considered Class D fires because they are metal fuels. And OSHA is going to require any manufacturer to put that flame pictogram on the containers of the metal, especially if the metals are in that finely divided form. Again, you're not going to see a GHS placard on a roll of aluminum or on a roll of titanium. But if it's in the powder form, if it's in shavings or turnings, yes, you're going to see some kind of flammability placard on it to let you know that there is a hazard associated here. One of the issues we see with these kinds of materials is because These kinds of materials, these metals are often used in building materials, often used in different kinds of metallurgy, metal forging, machining. This is where we tend to get the most common kinds of uh, turnings and shavings and powders and whatnot. An additional hazard of this is because they are involved in machining or metal forging, we will find that they are often coated in oil-based lubricants, and those lubricants themselves are also flammable. So you kind of have a 2-for-1 thing going here, where you've got a material that is flammable itself in the right circumstances, being coated and exposed in something else that is also flammable. These metallic substances will produce hydrogen with water, very similar kinds of reactions to what we saw with the alkali metals. We're talking about the metal reacting with water to create the metallic hydroxide and hydrogen gas. And any of those metals can kind of fit in for M. If it is aluminum, the equation is slightly different because aluminum hydroxide is not AlOH2, but rather AlOH3. But the same idea basically exists. We're going to see some sort of hydroxide, which is going to act as a corrosive base. And then we have hydrogen gas. That hydrogen gas will spontaneously ignite. And as it ignites, it will begin to ignite the metal sample underneath. Now, again, this kind of reaction is really only going to occur in those finely formed solid forms. Again, if I throw a big sheet of aluminum into a swimming pool, not a whole lot's going to happen. They will react, but they'll react pretty slowly because there's so much surface area that is not being tapped into. Because you got to think, with a sheet of aluminum, with a sheet of zirconium, with whatever, the more intact it is, the more the interior of that sample is protected from the rest of it from reacting. If I take that same mass and I turn it into a powder, now all of it is surface area. It all reacts at the same time. We get lots of hydrogen generation. We get lots of reaction as a result. So let's look at these individually. Now, magnesium is probably the one that we're the most familiar with. As a metal sample, it is in the second group. The second group is the second most reactive of the metal samples. So the alkali metals react with everything. They react with air. They react with water. They can spontaneously ignite in the proper circumstance. They react almost instantaneously with water. The alkaline earth metals right next to them, very similar. They are reactive. They will react slowly in cold water, and you will do this reaction. It's going to be one of those reactions where you put a magnesium strip into a beaker of water and you walk away for probably about 20, 30 minutes to actually see the reaction take place. In warmer water or hotter water, it will react a little bit more quickly. Magnesium is a pretty good reducing agent. Because again, like the alkali metals, the alkaline earth metals want to get rid of electrons. And so magnesium is very willing to give their electrons away. As we have seen, magnesium is a very highly combustible material. When it combines with air, it'll form magnesium oxide and magnesium nitride. Both will happen. So magnesium with oxygen will form the magnesium oxide, and magnesium with nitrogen will form the magnesium nitride. Magnesium nitride, when combined with water, makes magnesium hydroxide, which is a basic substance. The reaction that we are most familiar with when it comes to magnesium is this one that is being described here at the bottom. When it reaches its ignition temperature, which is right around 1200 degrees Fahrenheit, we'll notice two things. First of all, if we have a large sample of it, it will begin to melt. And the second thing is that upon melting, it'll immediately start to burn. And the burning of magnesium gives us a couple of things. First of all, it gives us a lot of heat. And it also gives us this very brilliant white light. So white, so bright that you actually are encouraged not to look directly at it while you are doing it. Because the intensity of that light can actually harm your retina. So, like I said, this is a somewhat familiar reaction to us. Most analyses, most demonstrations of combustible metals involve magnesium because it's easy to acquire, and the reaction itself is actually quite brilliant. Titanium. Titanium is another place where we see combustibility. Now, on the production side, titanium is a good bit more costly because it is not as common of a metal. And it's kind of hard to purify. As a building material, it is almost half as heavy as steel, but yet remains and retains all of the strength of steel. Where we see it used primarily is in the manufacturing of large automobiles and in aircraft. One of the advantages to it, especially for those machine parts, is that it is basically indestructible as far as chemical corrosion attack is concerned. And this also speaks to one of the reasons why it is kind of difficult to acquire. Because the titanium oxide in question, or excuse me, the titanium in question is really tough to purify because it's already reacted with the air. And so all titanium has a titanium oxide coating on the outside of it. That titanium oxide coating is very resistant to chemical attack. So where do we see it used? Well, we see it used for stuff that needs to go underwater. Where if the material is going into a place where the acidity might be a little bit off of neutral, the titanium oxide will protect the machine. We also see it used as a container for a lot of corrosive materials for the same exact reason. The corrosive material is not going to eat through it. But as you can see, one of the dangers of titanium is that in its powdered form, it is pyrophoric. Instantly ignites in the air. When it does, creates lots and lots of heat that can either cause a fire, spread a fire, or if the situation is right, could create an explosion kind of situation. So titanium, particularly in its powdered form, is especially dangerous. Now, in its bulk form, pretty useful. Again, where we have to be careful for it is in those situations where we have it in a powdered form or a shaving form, or if we're working with it and it's possible that we can cut it while we're working on it. Zirconium. Zirconium is, again, that's element number 40, ZR. Where we find zirconium is in the nuclear and steel industries. As with some other metals, this is not exactly one we come across super often. There are some rarity issues associated with zirconium. But just like we saw with the titanium, again, look at where zirconium is in relation to titanium. They are in the same group. Remember, elements with similar properties belong in the same column of the periodic table. Titanium and zirconium both are in the same column. They're in group 4 of the periodic table, which would be group 4B, I believe, on the cast numbering system. Like we saw with titanium, if we have it in the powder form, if we have it in zirconium dust, we've got a fire risk. We've got an explosion risk. Those particles can heat up pretty quickly just from their own friction. So again, the issues with it come with when we are working with it, do we handle it properly? When we heat it to a red hot temperature, then it will react with water. And so that red hot temperature, we're talking about 900 Celsius, 1650 Fahrenheit. So this isn't going to be something we just drop it in a beaker of water and it will start to immediately form hydrogen and ignite. It's not going to be the case here. Temperature situation isn't high enough. If it were to come to this, and we were getting this situation where we had hot zirconium in the presence of water and we were getting the hydrogen, there would be 2 ways that we could handle it. First of all, one way, we just take that gas, if we can vent it to the outside somehow and let that hydrogen just disperse into the atmosphere, that's probably the easiest way to go. The other one's kind of interesting, because it kind of seems counterintuitive. Why would treating something with oxygen help prevent the reaction from exploding? We already know hydrogen and oxygen, that's a combustion reaction. That seems like the opposite of what we want. Why would it be okay in this case, though? All right, trying to see who's thinking on Monday morning. Well, just like with the titanium, if we can get that zirconium to form an oxide, that oxide is going to have no issue with water whatsoever. So treating the substance with pure oxygen, because it is so hot, it's going to be susceptible to reaction. And it's actually way more reactive with oxygen than it is with water. So by pumping a whole bunch of pure oxygen, the oxygen is going to react with that hot zirconium and form the zirconium oxide. And that zirconium oxide, like titanium oxide, is virtually impenetrable to attack and not terribly reactive, which is why, again, titanium oxide is used for the production of a lot of stuff that can go underwater. Zirconium oxide would have the same kinds of effects toward water. It's not going to be reactive. Now, one of the differences Zirconium doesn't naturally form oxides the way that titanium does. And so titanium naturally had that oxide on it from the start. If we're dealing with zirconium in this situation, it's not going to. But introducing the oxygen would allow it to. Aluminum. Metallic aluminum on its own is never found in its pure state. Aluminum is far too reactive to find pure samples of aluminum. And that's largely been the case for the other things that we've talked about out of those first two groups of the periodic table. Can't find sodium by itself. It's too reactive. Have a hard time finding calcium by itself as well. There's some pretty good reactivity there also. Aluminum's the same way. Now, where we find aluminum primarily is in minerals, rocks. And so how do we get the aluminum out of those? Well, that goes back to chapter 8. Chapter 8, we talked about processes where we use acids to do extractions. Well, this is an example of one of those. We do an extraction using an acid. It gets the aluminum into solution. We can take that aluminum solution, do another chemical process to it, do electrolysis on it, do some electroplating, and get that purified aluminum. Now, the problem we're going to run into is that as soon as we take that aluminum out, it's going to react again with the oxygen in the air. But at least it'll be in a more purified form where we can do some things to it to make it a little bit more usable. So one of the things that we know about aluminum is that it is very malleable. And remember, malleability is that property of metals where we can pound it into thin sheets. We know one of these products, aluminum foil. If you ever looked at aluminum foil close enough, you always know that one side of the aluminum foil is shinier than the other. That dull side, that's the aluminum oxide side. That's the side that has the oxide on it. The shiny part has been treated usually in some kind of way so that more of the aluminum is actually exposed and not quite as prone to chemical reaction. But we also find it in commercial containers. We find it in building materials. We find it in aircraft construction because it is very, very lightweight, has a relatively low density as far as metals are concerned. Density of aluminum is about 2.7 grams per milliliter. The density of most other metals are in the 7s and 8s. So it's considerably lighter. We know it's also ductile. Remember, ductility is the property of a metal that says that we can draw it into wires. Now, as far as aluminum wires are concerned, we generally don't use aluminum for this purpose. Primary reason, again, is its reactivity. That aluminum turns into aluminum oxide. That aluminum oxide is going to create a good bit of resistance inside of the wires. Resistance is bad when it comes to electrical conductivity. It means that it's not conducting nearly as well as it should, and as it pushes through the electronic flow, it's going to heat up, which is going to cause some pretty good problems if you are looking at wiring. You don't want stuff getting warm. That's where fires can start. Because aluminum forms oxides relatively easily, it generally is oxidation proof. Aluminum oxide kind of takes care of the oxidation of aluminum. So from an oxidation standpoint, aluminum doesn't get oxidized very much because the oxygen's already done it for them. However, metallic aluminum is not safe from other kinds of chemical attack. It's very prone to corrosion. The aluminum oxide does prevent some corrosion. It does provide somewhat of a barrier for that acid or base attack, but it's limited. As soon as that acid eats through the aluminum, that's the end of it. The resulting aluminum that's left behind is very reactive toward acids. As we've seen for the other metals in this subsample, the dust and the powder are pyrophoric. And aluminum dust allows for, it burns pretty easily in oxygen. It does burn spontaneously when it is liquefied, so liquid aluminum. Where we see it in fireworks is primarily when you shoot up that firework, that trail that you can see that kind of allows you to follow it. A lot of that's aluminum dust reacting. Also, when it explodes and you see those trails coming down, kind of that orange reddish kind of color after the explosion, after the initial set of light, that's usually the work of the aluminum in the mixture. And so you can always tell when aluminum is featured prominently in that firework because you can usually see it for longer, as opposed to the ones that just, they shoot up, they make their color, and then they just disappear in this cloud of smoke. The ones that seem to hang around a little bit longer usually have aluminum in them. Aluminum can also be used for something called the thermite reaction. The thermite reaction is a reaction that will, between aluminum and iron, that will create molten iron as a result of the reaction. Thermite reaction was used for a long time in the railroad industry to repair track. You do a little bit of thermite, it would create molten iron, allow you to kind of, if there was a crack in the railroad track or some other kind of problem, you could use it to do short repairs because it didn't really require a whole lot to do. And if you can control it, it would drop that aluminum perfectly right, or not that aluminum, sorry, that iron right where it was needed to be. It was in the liquid phase, so you could kind of maneuver it and then cool and harden relatively quickly for that repair. Other things about aluminum, it is rumored that the Hindenburg, part of the reason it went up so spectacularly was that there could have been aluminum dust in the balloon, in the balloon's coating in particular, which would have, when the initial reaction, when the initial explosion happened, could have accelerated the burning of that Zeppelin considerably. One other thing about aluminum is if we do get that temperature high enough, even bulk aluminum will start to burn and will burn quickly. But we do have to have kind of a starting temperature. So, you don't have to worry about using aluminum foil in your oven. That temperature, 400, 500 degrees Fahrenheit, isn't nearly enough to get that kind of reaction going. But if we were at certain other kinds of ignition temperatures, then yes, we could get aluminum sheets, aluminum foils, larger pieces of aluminum to ignite quickly in those circumstances. So just to give you an idea about what that reaction looks like, I'm going to show this thermite video here, and it's relatively short, but I want you to see kind of how quick this reaction can transpire. So one thing that's remarkable about the thermite reaction itself is how remarkably simple it actually is. So what they have in there is iron-free oxide, which is basically rust, and aluminum powder. And they're going to use a strip of magnesium here to act more or less like a fuse, just to provide a little bit of energy to kind of kickstart the reaction itself. So you can see that you put the magnesium ribbon in there now. So again, 3 ingredients: iron-free oxide, aluminum powder, and this strip of magnesium. And he's just going to use a torch to light the magnesium. So there's that bright white light. And there is the piece of iron, molten iron, that was dropped out of that reaction. So it's just a little terracotta pot that they put a small hole in the bottom of. And so you can see how this would be useful. There goes the iron down to the bottom there. You can see how this would be useful in a very fast-acting kind of situation. If you could figure out how to aim where that iron was going, it's going to very quickly produce iron that can meld with the steel.
Grammarly does more than catch errors. With Grammarly, you can
And melding with the steel, repair whatever problem was present in the metal itself. Looking at metallic zinc, zinc primarily exists in the forms of zinc sulfide, ZnS, or zinc carbonate, ZnCO3. So, like we saw with the aluminum, generally we have to get it out of its ores, out of rock and other mixtures in order to get the purified zinc. Other impurities that exist in the ores themselves can make this process even more difficult for the extraction and purification process. Where we see zinc used probably the most often are 3 things: galvanization. So this isn't as common of a plumbing practice now as it used to be, but using zinc to coat the steel pipes to make them more corrosion resistant was a very common plumbing attribute. There are still some houses around that have galvanized plumbing. Mine is one of them. The problem with galvanized pipes is that they do eventually wear out, and they when they do, it can be quite messy when they start to break and degrade. We find zinc used in the production of brass. Brass is basically an alloy of zinc and copper. And we also see it used in dry cell batteries. So These would be pretty much any of your alkaline kind of batteries, AA, AAA, those button batteries that you use to power watches, hearing aids, so on and so forth. Those are the three primary purposes: galvanized piping and other galvanized machine parts, brass, and batteries. Now, as we've seen with the others here, their primary danger from a flammability standpoint is their pyrophoric natures if they're in the dust form or the powder form. Again, if they're not in either one of those forms, we tend not to see a whole lot of danger with them. But if they are in dust or powder form, they are pyrophoric, they are going to be especially flammable. So in these last few minutes, we're going to switch gears here real quick. And we're going to talk about some ionic hydrides, which are not necessarily flammable, but they belong in this category because they happen to be usually quite reactive with water, and their reaction with water is what actually drives their inclusion here. One of the reasons why they are useful is, again, we're talking about some powerful reducing agents. So these are things that are going to lose their electrons quite easily as part of their chemical reaction. Now, while there are 10 ionic hydrides, they tend to kind of fall into a series of categories. And so those categories that we're going to talk about would include just simple ionic hydrides. So, for example, lithium hydride, LiH, sodium hydride, NaH, and so on. Hydrides are not terribly common. What we're talking about with hydrides are the hydrogen atom forming a negatively charged ion instead of the positively charged ion that we're used to. And we only see this phenomenon occur when we have strong reducing agent elements reacting with that hydrogen. So it takes a lithium, a sodium, a calcium to force that hydrogen to take on electrons. Usually hydrogen is much more comfortable giving electrons away. So these hydrides represent half of those ionic compounds I was talking about in the previous slide. So that's one form of an ionic hydride, just a simple metal hydrogen put together. There is another class known as the borohydrides. Borohydrides are basically kind of the same things, but what we see is that the boron atom has inserted itself in here. So we have lithium borohydride. We have sodium borohydride. We have aluminum borohydride. Again, remember what the primary uses here are. We're taking these are very common reducing agents. These are things that want to get rid of their electrons. And the part that is really looking to get rid of the electrons are those hydrogens. Because like I said, hydrogen doesn't like being a -1 charge. It'd much rather be either 0 or positive 1. So by having a -1 charge on it, I've got something that's very willing to give away electrons. Please take these away from me. And so these substances are very reactive as a result. And then the final class of hydrides here are aluminum hydrides. And so we've got a lithium, aluminum hydride, and sodium aluminum hydride as well. These ones are a little bit less common. What we're seeing here is aluminum basically acting in the same way that boron does because they are in the same group. But there's a rarity feature here. This is not nearly as common. The borohydrides are far more common than the aluminum ones. Where they're particularly dangerous is in their water reactivity. All of those hydrogen -1s turn into hydrogen gas. And so when it comes to their storage, you can't expose them to water. You can't even expose them to humid air. We often will have to store them in tightly sealed containers, usually covered in oil or some other kind of inert environment because of their risk of fire and explosion. So this is where we will stop for today. On Friday, remember Wednesday's our exam. On Friday, we will finish out this chapter and we're going to be talking primarily about water reactive substances and some of the nasty stuff that can happen when these things encounter water. Have a great day.